Hello, everyone. My name is Kristen Mulheron, and welcome to the next webinar in GoProto and Re3D Tech's monthly office hour series. Today, we'll be talking about 3D printing with MJF through the complete product lifecycle. HP's MJF technology is arguably one of the only technologies that can address the complete product lifecycle. This is important because that means you can prototype and take a part to production all using the same technology. There's really nothing quite like it out there. With that said, one important distinction about this webinar series, if you haven't attended one before, is that we create the content based on your questions. It's intended to be different from your typical webinar, and it's designed to be more interactive. You'll notice when you register that you're required to note that you were what you're hoping to get out of it today. Well, we've taken those questions and comments and used those to craft the content we'll be discussing. Some of these questions are listed on the slides themselves, but I also strongly encourage you to submit questions to the live Q&A throughout the webinar. We want this webinar to be more conversational, so don't wait until the end to submit your questions. Before we get started, I want to give you a quick introduction to GoProto and Re3D Tech. GoProto and Re3D Tech recently combined under Core Industrial Partners to form one of the largest and most complete custom rapid manufacturing companies in the US. And just last month, they also welcomed Phoenix Proto Technologies to their platform, which expands the team's prototyping and production capabilities even more. So with that said, let's introduce the speakers for today's office hours. First up, we have James Teuber. James founded Re3D Tech in 2016 and partnered with Core Industrial in 2021. He's now the Director for Additive Market Development for the new combined company platform. Up next, we have Wes Kramer. Wes is a 3D application engineer at HP. He's a leading industry expert in fine finishing techniques for multi-jet fusion parts, and also has a deep focus in technical areas such as digitally applied 3D textures and mass customization. He helps enable never-before-seen end-use MJF applications that raise product value and set designs apart from the competition. Welcome, gentlemen.
Thank you, Kristen. Very excited to be here.
Great. So let's go through the topics that we're going to cover today. So first up, we're going to give you a real kind of general overview of multi-jet fusion. Essentially, why should you care? Then we're going to go on to the topics that you submitted today. We'll give you a quick background on polymer 3D printing for the complete product lifecycle. Essentially, when does it make sense? When are you going to use it versus injection molding or some other traditional technique? Then we're going to go into a quick poll, and so we can decide how we're going to prioritize the remaining topics. So remaining topics being, what are the material options? What do we need to keep in mind regarding part design? And then what are the finishing options? We'll do that poll, and the top choices are where we'll prioritize our time. We've then also saved a big chunk of time at the end so that we can dive into kind of the specific hurdles that you personally are experiencing. And again, we'll base that off of a poll on the most common topics. But first, let's get to multi-jet fusion. Why should we care? Wes, do you want to take over?
Yes, I would be happy to. Thank you. Thank you again, Kristen. So multi-jet fusion, maybe some of you in the audience have heard of this technology before. Maybe it's new to some of you, but I want to make sure we all have kind of a baseline foundational understanding of the technology itself, and what brings us here today, and why this technology is applicable at different points along the product lifecycle. So some history or some context behind the technology. You know, HP, when they decided back in 2013 or so to invest in 3D printing or additive manufacturing, they didn't want another prototyping solution out there on the market like most other 3D printing technologies. When they took a look at the market size of 3D printing versus the entire market size of manufacturing as a whole, they realized that 3D printing was really just kind of a small subset of what overall manufacturing could be. So when we decided to create technology, and it was first introduced back in 2015, it really was with the goal of addressing the manufacturing market and not just prototyping. And so that being said, our technology, what it is built to do is to be one of the first true additive manufacturing production platforms on the market. So what does that mean in terms of capabilities? It means that we have very high throughput compared to other 3D printing technologies. We can make a lot of parts very quickly. We can do it at a cost that's very competitive with traditional manufacturing techniques like injection molding. There's a number of factors that contribute to how we get to that low cost per part. We are very repeatable in our process in terms of dimensional accuracy and mechanical strength, properties like that. We have good isotropy, which is strength in all directions on our parts, which is not always very common in 3D printing. And we have, at the end of the day, very, very excellent materials and material properties for end use applications. So we're not just making parts that look great, we're making parts that are truly functional and durable and can actually serve end use applications. So it's kind of a mixture of those different components that our technology brings to the table. And it's really what is allowing this technology to be more of a production system and not just another prototyping 3D printer that you've seen for the last several decades.
Great. Anything to add, Jim?
No, that's what we identified when I first heard about this system. I said we can build a business around that. I was the second person to put a deposit down on the HP in North America, sight unseen, because I'm like, well, I didn't want to compete with the service providers out there that were focusing on the prototyping spectrum end of the spectrum. We wanted to really start focusing on production. So, and luckily, HP came through for us, Wes, and has put a great product out there for us.
Great. Okay, so now let's move on to a quick summary essentially on 3D printing for the complete product lifecycle. I think it's important to touch on, most people know 3D printing for prototyping, but there's a much broader spectrum of where it can be used. So we'll start with simple, when does it make sense?
Yeah, so what we've learned with our customers and when it makes sense to move into 3D printing for prototyping has been around for many years now. But when you start looking at when it makes sense is when we can apply and change geometry. A lot of times people come to us with a part file and say, hey, can you print this? And yeah, we can do that. But when we can be part of that development process and we can add value into that part and that application by doing some of the things you see here, lightweighting, when we can take 4 or 5 components of a part that would require tooling and assemble them into one part file and print it. And some of the other, either ESD or fire retardant materials that are coming online, or energy absorption with some of our elastomeric materials. And then when does it make sense to move past that prototyping phase into bridge production, when you want to validate that application in the marketplace, make sure that it is, hey, you've got a great idea. Does the market think the same way? So they can, we can really start cranking up that unit count without having to go into traditional tooling at that point in time. So this is a graph that is out there. Many people have seen this. This is just basically looking at when it makes sense and when is that tipping point when an application kind of moves past what additive can bring to the table, and when we need to move and think about bringing that application into more of a traditional manufacturing footprint and product lifecycle. But as you can see, that yellow line, as we're introducing more material options and the process is getting, and HP is continually improving the process and improving the software. And they're doing that internally with how we're managing the speed of the print and all the thermal properties and dialing that all in. That breakpoint line is continually sliding out to the right side. So, what we try to do is we try to understand the application. That's what we bring to the table is, let's talk about that application. Let's talk about what its needs are, and then get you into the right path. And a lot of times our conversation revolves around additive manufacturing for production, and how can we bake in value into that part design that we can move that line continually, keep pushing it out to the right side of this graph. And now this is a graph, again, that a lot of people have seen is when does it make sense? We have the unit count on the left-hand side, and then the product life cycle here along the bottom. And a lot of people are familiar with using additive manufacturing or additive or 3D printing in the prototyping phase. they need to understand just the fit and function and get some basically get that part in front of investors. There's all sorts of different ways to understand and use additive for that prototyping phase. Now, when we moved into bridge production, like I said, maybe we're validating the market. Maybe you want to get to market faster. Speed is key in so many environments now in the world. You have to be first to market. The first guys usually win. And if we can move that application into bridge production and then design it for additive, but if not, if it's going to be designed for traditional manufacturing eventually, when that enters that yellow part of the graph here, well, if we can get parts in people's hands and that application into the market faster, that's gonna really help solidify your position in the marketplace. And then when we move into full-scale production, if we can add enough value into the application by combining multiple assemblies into one, or we lightweight that part, or we design better functionality into that part that you can't do with traditional manufacturing. When we can do that, then we can move that into full-scale production additively. And one of the things that really resonated with a lot of our customers is that long tail production. That when that product is done, and there's a lot of scenarios where companies have to keep warranty parts in inventory for 10 or 15 years. And we've heard from many customers that, hey, they go back to that original manufacturer that made those parts and they're out of business, or their mold is, they can't find the tool that they made the parts from. How do they handle that? Well, when we can have that discussion about the whole product life cycle and design in end of life obsolescence for spare parts or for warranty parts and qualify that in the front end, we bring a lot of value to the, to that conversation about how we're going to handle a digital inventory for that spare parts, that instead of having them in a warehouse, for years and years, you can just have a digital inventory for those parts.
Great. Are there any questions from the audience? We did get one question. We will answer that when we get to the material section. If there's anything else on these previous slides, now's the time to ask. Otherwise, we'll move on. All right. So there were three primary topics that came up when you registered for this webinar. We lumped them into these three categories, and I want to go ahead and do a poll so we can figure out exactly how we should prioritize these topics. So what's the number one thing you're hoping to get out of today? Material, what are the material options? What should we keep in mind regarding part design? Or what are the finishing options? So we'll give you a couple of minutes here to fill that out, and then we can start. All right. Oh, there's still people answering. Looks like there's a pretty strong preference for the material options. So we'll start off with material options. We'll then go to what should we keep in mind regarding part design. And then if there is still some time at the end, we will get to finishing options. All right, so what are the material options? Here we are. Wes, do you want to go ahead and kick this off?
I would love to. So what we're looking at here is kind of one side of what we have to offer with our multi-jet fusion platform in terms of materials. And this is our range of polyamides that we offer. And if you are familiar with polyamides, and you know that it's basically a type of nylon. So these are very, very strong, durable materials, on the level of injection molded quality in terms of isotropy and mechanical properties and strength. So on the left side, what you're looking at is two different types of PA12 material. And so again, both nylons, and what you see here is one is white and one is gray. And so most of our technology, we're printing gray parts. We have this black fusing agent we use in the process, printing on our white powders, and you get the superposition of those two things, and what you have at the end of the day is gray parts. But just recently, within the last few months, we released our white printer, which actually prints white parts. And so the only material we have available on that platform, the 5420 white platform, is going to be our white PA12. So this is kind of the most, I would say, well-balanced material that we have in the portfolio in terms of rigid materials, best balance of part properties and cost, and other things. So we see a lot of customers using PA12. We take a look at PA11. That is going to be very close to our PA12 in terms of properties, but it's going to be on the more ductile side. So a little bit more toughness here, a little bit more flexibility. And another interesting thing about this material is that it is renewably sourced from castor oil. And so whereas most plastics are petroleum based, this is going to be castor oil based, which is another interesting thing. If sustainability is important to your company, definitely a material that you would want to consider for those purposes. And then last but not least, here we have a glass bead filled nylon. This is going to be our PA12 glass beads. And this is now going to be on the other side of that spectrum, more on the rigid side compared to our PA12 and PA11.
Wes, one of the questions that's come in that I think would be good to answer here relative to the materials is what kind of tolerances can the MJF process hold? Does that vary from the materials? And in general, what are the tolerances?
Excellent question. Excellent question. So with our materials, we will experience slightly different tolerances for the different materials, but it's all in the same general range, I would say, especially when we are looking at our rigid materials. So with our PA12, just as an example, what we typically reference is what's called the International Tolerancing Grade, or IT grade standards. And what this is basically a range of tolerances for different sizes of nominal dimensions. So as you can imagine, the bigger a dimension is that you measure, the wider that tolerance might be as a percentage of that dimension, right? So if you reference the IT grade standards, there's different levels. And I would say we are most comparable to IT grade 13. So feel free to look that up, and it'll give you a nice look at what those tolerances are. But I can tell you for a dimension around 50 millimeters or so, kind of on a little bit on the smaller side, you can expect to see plus or minus, within 0.2, 0.25 millimeters of that nominal dimension.
And do you see any shrinkage with this process?
So with all plastics, with all thermoplastics, we do have some shrinkage in the process. That is something that is factored into our process. And so we have scaling factors that are applied pre-print based on the properties of the parts and a lot of historical data that we've measured in the past. And so we do have ways to compensate for that shrinkage and get very, very close to our nominal dimensions.
So we do still have to move to the elastomers, but I wanted to throw in this one last question here is, are any of these materials recyclable?
So they are actually all recyclable, which is very, or somewhat unique for 3D printing. We have a lot of photopolymer resin type 3D printing platforms on the market today, in which it can be very difficult to recycle those materials because they are technically thermosets. But the beauty of thermoplastics is we can always kind of regrind and remelt these materials to be used in other products. So not only can we recycle the actual parts and use them in other products in the future, which is being done today, we also have unused powder that's not used in the process, and we can recover a very large percentage of that unused powder and use it in subsequent prints. So a very recyclable, very eco-friendly process, I would say. Excellent. So here is kind of the rest of our materials in the portfolio right now. Before getting into the elastomers, we have one more rigid plastic that is out there, and that's going to be our polypropylene, which is a genuine polypropylene. A lot of different technologies out there have kind of a mock polypropylene or something that's similar in properties to polypropylene, but isn't genuinely chemically polypropylene. And why that matters, say you want to injection mold a large plastic polypropylene component, and this is, super commonly used material in automotive especially. So imagine like a fascia or something that's this big, broad polypropylene injection molded part. But you have all these complex little features or sensor mounts, things that need to go on that B side of that surface that would be impossible or very difficult to include in that injection mold. What you can do is, because these are chemically identical or chemically compatible, you can actually thermally weld our 3D printed material onto that injection molded material. And it is compatible with each other, and you can get a very nice durable bond between those two substrates. So interesting things there. It's our lowest cost material in the portfolio, very chemically resistant. The one drawback, we talked about dimensional tolerances previously. This is going to be a little less accurate than the polyamides, a little bit harder to control those dimensions. So that is all the rigid materials. And then we also have elastomers that we offer. We have two different types of TPUs. One is available on our 4200 platform, which is kind of our legacy platform. And then our newer 5200 platform, we have a different TPU. And so BASF TPU is going to be on our 5200 platform. Lubrizol TPU is going to be on our 4200 platform. And then we also have a TPA, which is another type of elastomeric material, also available on our 4200 platform. But at the end of the day, these three elastomeric materials, I would say, are similar to kind of like a hard rubber. If you're familiar with a short A hardness scale, a lot of these materials are upper 80s, lower 90s short A hardness value. And so that's what the base material is, but what we can see is through different design techniques, we can make that overall structure much softer, especially with what we call lattices. And maybe we'll get to that a little bit later in the webinar.
Great.
And then
Okay.
go ahead, Chris. I just want to make one quick point about the materials, that the advantage of what the system brings to the table is you can do that prototyping phase in the same material set, all the testing, all the chemical testing, all the strength testing, with the same material that you're going to be moving into production with. So that's a really big advantage that this process brings to for our customers, that if they're going to move into additive production, they don't have to guess. There's not that, takes that guesswork out of it by using these material sets.
Okay, before we move on to part design, there are a bunch of questions here I want to get to. One thing you didn't touch on, Wes, when you first introduced MJF, is that it is a powder-based system. Can you comment real quick on what that means with regards to the support structures?
Yes, so there's a lot of advantages to using powder-based systems. And if you're not familiar with the different types of 3D printing technologies out there, powder-based basically means that we lay down a very thin layer of plastic powder that's very, very fine. Almost, you know, like the consistency of flour, I would say, or maybe a little just slightly coarser than that, or, you know, very finer than sand though. So we lay down a very thin layer of powder, and then we selectively melt that powder based on what parts we're printing in a layer. And so that's kind of what it means to be a powder-based system. And so one of the big advantages, and I appreciate you bringing this up, Kristen, is that because your parts are basically surrounded by powder as they print in the process, many 3D printing technologies out there, you have to print support structures for overhangs or different features to support that material against gravity as you're printing. Because everything is supported by that surrounding powder, we call it self-supporting, so you have no need for support structures in the 3D printing process. And so what that gives us is a better finish on our parts. It's less manual in a lot of cases because you don't have to remove those support structures afterwards. So that is a huge advantage that we get from being a powder-based system.
And another big advantage of a powder-based system is, for us as a service provider, we're exposed to we could have 100 different parts in one build envelope. And what we do is, the reason why this is a great production system is by optimizing that build space, by putting and positioning those parts so we can pack that build effectively. We could have 10 different customer orders in one build space. So that really helps drive the price point for all those parts. We can spread the cost of that build through all 10 of those orders instead of just putting all that cost into that one order for bringing those parts. So that's something that powder bed system really helps drive that price point down too.
Absolutely. Yeah, we talked about throughput and being able to print a lot of parts very quickly. You know, self-supporting, meaning you can print at, angles like this and you don't have the support structures underneath. But as Jim was alluding to there, we can stack parts on top of each other in the build as well. And we can fill up that entire three-dimensional space. So in certain applications, say you're printing dental aligner molds, you can fill up that build with nearly 400 of just that, you know, type of geometry. And in one build, you have 400 or 500 parts that come out of that. So very, very key to enabling that throughput we had talked about earlier.
And we do have an image of that actually, the show when we get to the part design section here in a little bit, that really demonstrates that really
And
well.
I always call it like the Jello mold. It just kind of, all the parts are suspended and the unused powder just kind of floating around in there. So it's pretty neat to see.
So based on that conversation with it being a powder-based system, can you make a quick comment on multiple materials? I think with the powder-based system, obviously we can't do multiple materials.
Right. So what you're not going to see anytime in the near future is the ability to kind of blend between two materials in that one print, right? But what is interesting to think about is we actually apply in our process agents. We call them agents. It's basically like ink. If you think about printing on paper, we apply agents or ink to our powders with our HP, you know, print heads that we have been using, you know, in developing for decades. There is the potential in more of the near term for using those agents to modify certain properties selectively within a certain part. So it's definitely, you know, something that might be a ways out before we start seeing that implemented in some of our products, but it is something that is absolutely something to think about or theoretically possible, and could be not terribly far away. So even though we might not have two different types of powders in one print and one process, there's ways to kind of modulate the properties based on the agents we applied potentially. But even right now, something that we can do is we can modulate the properties based on the design itself. So we think about lattice structures, for instance, with our elastomeric materials. You know, this basically is something that's going to act like a sponge or like foam. Just by changing the thickness of those beams of that lattice structure, you can completely change the property of that part from being more stiff to being softer. So that can all be done in one part and one print with one material just by changing the design. So there's still tons of different possibilities out there, even without the ability to do two or more different materials in one single print.
Okay, one other question that came in way earlier was, are there any food safe options here, materials?
Great question. So this is something that we do not have a standard solution for right now for food contact approval. But based on your application, that is something that we might be able to discuss, because there are some things in development and some things that we can address, and there's others that we cannot. So if you have a specific application in mind, it's a little bit higher volume production, but it needs that food safety or food contact, I would definitely encourage you to reach out and we can kind of talk about that in more detail.
All right, one last question before we move on, and we will get to some of these other questions at some later sections, so don't think I'm ignoring them. Can you just do a quick comment on surface finish?
Yes, so different materials in our portfolio have slightly different roughnesses or surface finishes associated with them. But at the end of the day, because it's a powder-based system, you're going to have this slightly grainy surface. And so it's going to be like almost the texture of a fine sandpaper almost. And so it's going to have this kind of satin sort of finish to it. But what we're going to talk about hopefully a little bit later is different finishing techniques, or what we call post processes, things done after the printing process to modify that surface. There's a lot of different possibilities out there. So even on this screen right now, when we're looking at that TPA and that BASF TPU on the left and the right, those parts have been vapor polished, which is a process where we chemically etch the surface and it smooths it out, and what you get is something that is very, very close to an injection molded surface. So different options and possibilities there, but right out of the printer, what you have is something that's a little grainy. But what's nice about this, if you think of other 3D printed parts, is we really don't see layer lines that much. We print at typically around 80 micron layers, which is super fine. And so you're not going to see those discrete layer lines like you would in, say, an FDM process with your desktop printer.
All right, let's move on to part design. We've got quite a few slides here, so we'll go through these pretty quickly. Wes, did you want to start this?
Absolutely. So just like with any sort of manufacturing technique, you have to design for the manufacturing process, right? So in injection molding, what you're thinking about is trying to keep uniform wall thickness everywhere. How are you going to eject these parts from the mold after they are injected into the mold? And so there's decades and decades of research and development that has gone into how we think about designing for injection molding. Well, just as you have to put yourself in that mindset for injection molding, you have to do the same thing when you think about additive manufacturing, because there are different considerations or different things that we need to think about when we're 3D printing versus, say, injection molding. And so there's a lot of freedom that 3D printing gives us. I would say it leans towards it giving us more freedoms than more constraints compared to traditional manufacturing. But there are things, nevertheless, you have to consider. So, for instance, when you're thinking about injection molding, a lot of times you might, or CNC machining, you're thinking about minimizing machining operations. And so the more complex a design gets, the more expensive it's going to be. With 3D printing, it's a little bit different. The more complex the design gets, it doesn't add any cost to the actual manufacturing. And we can print very highly complex designs. What we are really trying to do, as much as possible, is reduce the amount of material we're using in the process, because that's going to ultimately drive the cost of that part down as low as possible. So we're thinking about lightweighting here. We're thinking about removing material, and we're thinking about, how it's going to perform thermally in the printer as well, especially for our technology. But there's different considerations, different things to be aware of. But at the end of the day, we get a lot more freedom out of additive manufacturing than we do with something like injection molding.
And then one quick point I'd like to make too, that people aren't as mindful of, you have to, like Wes was saying, you have to design for the process. But you also, when we talk to our customers, and if we really want to optimize the application for additive production, we have to talk about post-processing. How do we, because if we have to design a part and we print it, we have to remove that powder. And there's certain things, if we have dead end holes or cavities that we have to manually get that powder out of, it's going to drive that unit cost up because you're going to have labor involved. So when we can design the part to be automated or post-processed, we have a lot of automation equipment here that handles the parts after they're printed. If we can design some optimization into that, not only the part functionality, but also the manufacturability of it, that's where we bring the value into the equation for the parts.
All right, let's quickly go through the different things to consider.
Absolutely. So, we won't spend too much time looking at the injection molded side. I'm kind of assuming that a lot of people are familiar with how things have been done in the past. But taking a look at 3D printing, one of the first considerations is build direction, or how you're going to orient this part in the build. And so if we print surfaces that are really close to horizontal but slightly off, what you might see is discrete layers, because basically you have to choose where you're going to start that next layer from the previous. And so that might affect something like surface finish. So if your priority is cosmetics, you're going to want to pick the best orientation to minimize that type of imperfection on the surface and to make the most uniform kind of surface finish possible. So you can optimize for finish with the build direction. You can also optimize for things like accuracy with build direction. And so typically, in order to get the most accurate parts, we want to print those critical dimensions flat in the XY plane. Not only do we get a little better resolution with our print heads, with our incredible, resolution that HP is known for with printing versus that 80 micron layer that we get. But thermally, we typically see parts fare a little bit better when printed flat as well. And then when we're talking about strength, usually again, printing those parts in the XY planes, we're going to have the best properties. But ultimately, I've seen a lot of parts come out of our process. Most geometries, you're going to have pretty excellent strength and properties regardless of the direction that you're printing in. So certain, thin, flat geometries, finer features, you might have to really consider how you're printing the parts and the orientation. But I think a lot of geometries are going to fare pretty well regardless. So print orientation is pretty big, and this also ties into what we call, changes in printed surface area. So this is a great depiction of what we're talking about here. So you need to print some sort of cover for something, right? And the most accurate way to print it might be flat, and what you need to avoid though is going from printing very little material to all of a sudden going to printing a bunch of material all at once, right? And so here, if you have a flat base, it's a very sharp transition from a small amount of printed area to a very large amount. And so that can potentially cause some print defect issues. But ultimately, I've seen a lot of parts printed just like this and come out pretty incredible as well. So, I would say compared to other technologies, we have a very high tolerance for these sorts of things. But you can consider doing something like a dome shape in this case, which is going to definitely increase that uniformity of your printed area as you go up in the build, or that corrugation effect is another example of how you would increase that uniformity as you build your parts. And then this is one of the most critical factors to think about when you're trying to optimize your builds for cost, and that is packing density. How many parts can we fit in a build? How efficiently can we pack these parts in the build? Because at the end of the day, if you can only fill up 1 or 2% of that volume with parts, you're losing out in a ton of efficiency of being able to print other things in there. And so what we talk about is nestability, the ability of parts to fit together in the build. An example my colleague uses all the time is printing, Lincoln top hats versus printing witch hats, right? The top hats aren't going to stack on top of each other. They're not going to nest well in the build, but those witch hats are like cones and they're going to stack on top of each other, and you're going to be able to fit a lot more of those in a build. So when you're looking at your geometries, you're trying to think about how many of those parts can I fit in the build? Can I do anything to make them nest or fit together in that build space more efficiently? And that's going to drive your costs down by a very significant amount.
And then one thing that we differentiate ourselves from the market is we try to have that human touch where we are asking those questions a lot of times. We don't have an instant quoting platform. We want to make sure we get our eyeballs on your application, understand if it's a cosmetic part, are there high tolerancing areas? So we know how to take advantage and optimize that part's orientation to get the results that you might not get if you're just throwing it out there on an auto quoter.
Yep, I think that's super critical. All the things we just talked about, it's not super trivial information. It does take a little bit of experiencing, knowing how to design for parts. What tiny tweaks can make, in some cases, all the difference in terms of the costs are going to be quoted. And so having that human to human interaction and kind of working together on how can we make some slight tweaks to this to make it a little bit more efficient is going to have a huge impact at the end of the day.
So 2 questions that kind of touch on what you guys spoke about is, does your slicer automatically orient the parts, or does it need to be done manually? And can that small to large surface transition be avoided by orienting the part at an angle, or does that come with its own set of issues?
So I'll address the second one first because I think it's a little bit simpler to address. Yes, you definitely can reorient the parts, and that's going to be a quick and easy way to make that layer to layer transition more uniform. But we talked about, sometimes it's more accurate to print parts flat in the XY plane. Sometimes you get a little bit better mechanical properties printing them flat in the XY plane. So there are some minor trade-offs. At the end of the day, again, though, most geometries I'm going to say are pretty robust in our system. And so you're going to see some pretty high quality parts regardless. So yes, that's definitely another tactic you can employ. In terms of automatic packing and nesting parts, HP has a free software that comes with the system called SmartStream. And there is some auto packing features in that software, but it is limited. And so what it does is it makes a bounding box around your part. and it packs the parts based on those bounding boxes so that those bounding boxes aren't colliding. And so if you have complicated geometries, say like that witch hat again, it's going to build a box around it and it's going to nest them next to each other like that. There's premium software options on the market like Autodesk NetFab or Materialize Magics. That's going to be a lot smarter, and it's going to actually read that geometry, and it's going to be able to nest that witch hat inside the other witch hat, so to speak. And so what you're seeing here, this example here, I believe was packed with Magics. And you can see the really tight nesting you get, and that was done in an automatic fashion. And so you select, I want the part space this much. I'm giving it this much freedom to rotate around this axis. I need this much space from the walls. You click go, and in a couple minutes, you have your build nice and easily packed for you.
And then just one other point to that too, when we're putting our builds together, we can lock the orientation that we want that part printed in. Even though it's going to auto nest that part, the orientation of that part is going to be locked in. So we know if it's a cosmetic surface and that needs to be facing down, we can do that. Also, another point is, like you're saying, that big box, it would be cheaper to print flatter if that was the only part you're printing, because if you put it on an angle, the build height really drives that cost. The higher the build is, the higher, the bigger that part takes in that build envelope, it's going to cost more to make. But being a service provider, we have access to hundreds of parts every day that we can put into that build space. So we don't have to, again, like I pointed out before, we don't have to assign all that cost of that build to that one part, where if someone was doing this individually, they might have to do that. But for us, we were able to drive that price point down because we can surround that part with smaller parts to optimize the build space.
Okay, one more slide before we move on to the next topic.
Right. So this again is another really interesting concept when it comes to designing for additive. And it's something that's unique to us, right? And this is an example. This was a real product, in one of our printers. And so there was this duct that was traditionally designed, and it had to be molded, from 5 or 6 different components. And so each of those components had to have its own mold. And then afterwards, everything had to be assembled manually. And so you can imagine, especially in a low volume production scenario, which this is definitely what this fell into, it would have been super expensive to, first of all, manufacture those molds for each of those individual components, and then to have someone manually assemble them. With 3D printing, the first thing that we did here is we just consolidated all those parts. We combined them, unioned them all into one part, and printed it all as one part. So we don't have to make any molds in the process, actually. And we don't have any manual assembly time after printing as well. So in this case, we already significantly reduced the cost, but the product was ultimately going to be performing this exact same as the first injection molded or traditionally manufactured prototype. Now we get into what's super fascinating about 3D printing and the design complexity that we can print with when we think about optimization and some of the really interesting new advancements on the software design side of things. And so this was a process called topology optimization, where they took the kind of overall bounding box of the fluid condition that needed to occur for this product, and they ran it through this simulation to basically optimize this geometry to increase flow rate and to reduce the amount of turbulence. And so if you look at that geometry, no designer would intuitively be able to design something like that. Only through simulation and software would you get this really interesting organic shape that not only is going to print cheaply with minimal material in one unit, one consolidated unit, it's also going to increase the performance of your product. And this is super important, not just for increasing the flow rate by a small amount, but think about if air can travel more easily through a channel, that's smaller blowers that you need. That's in electric vehicles, less battery power that you need to do that. And so all of these things combined together stack up and end up being a huge factor in terms of the performance of these systems, the noise that they generate. And so definitely a really interesting use case here that we love to talk about all the time, where we not only made it cheaper, but we increased the performance of the product as well.
Great. So we've got 15 minutes left, and in that 15 minutes, we're going to jump to, we're going to skip over the finishing options and go to your biggest obstacles. With the finishing options, we did cover that topic in quite a bit of detail in a couple of the previous webinars. So some people have asked as well if this will be available afterwards. So this webinar and those previous webinars are all available on the Re3D Tech's YouTube channel. So you can get a lot more information on the finishing on the ones that happened just a couple of months ago. And then you'll see this one up there in about a day at maximum. So one more poll. What are the biggest obstacles preventing you from adopting additive for end use parts? We'll take this as a priority as well of how we answer them, and we'll do a little bit of a speed round with this remaining time. So go ahead and put your votes in for what your biggest obstacle is. All right, I think we got everyone in there. Right, so cost is going to be the first one. I think we can get to some of these questions that were in the Q&A as well. And so if you guys want to address cost, one of the other questions that's come up is major cost factors mentioned. Is material volume less of a factor than cycle time to make the part drive costs? And then there's also a question on the cost comparison between the materials before.
Yeah, so one of the ways that we can address cost, like Wes was saying in that last use case, how we can optimize that part for, instead of having to do it traditionally and have 5 or 10 different molds to make that application, you can design that into one unit. And that's a way that we can really drive down costs. And then also, again, what Wes was alluding to, is that enhanced functionality. When, that part might cost a little bit more, but if it's adding a lot more value to that application's functionality, then it really brings that value to the equation versus just, worrying about that unit cost. It's about how it's performing in that specific application.
Absolutely. And, we talked about before that curve, right, of different volumes and where that makes sense to move to additive manufacturing. And so, if your volumes are low and you have a very high mix scenario, say one assembly, you're making 200 of them in a year, or even up to, in some cases, like 1,000, 10,000 of them in a year, but that one assembly has 80 different, small plastic components on it. Is that really, 80 different molds you want to make for such a small volume of that product? There's just, apples to apples, a really, quick and easy economic comparison you can do where it really does make more sense to 3D print. And then you asked Kristen about, different costs of the different materials. Yes, there is some differences there. It has to do with the, kilogram to kilogram, cost of the powder itself, but there's also different factors like the refresh ratios that we use, which is the amount of fresh powder to reuse powder in the process. But PA12 and polypropylene are going to be on the lower cost side, and then the elastomers are typically you're going to see on the little bit higher cost side if you had to do a comparison.
I think another topic here. Oh, excuse me. You guys can hear me, right?
Yep.
I think another topic here that kind of fits into this category is what's the break-even quantity for time and material between molded and printed for something like this for a manifold part? I feel like this fits into costs as well.
Yeah, so it's very, very difficult to say without knowing the size and the shape of that part. Size is a huge, trying to talk about a break even in terms of part volume, right? Because if it's a larger manifold and you can fit 5 in a print, that's going to be a super different break even volume than if you can print 500 in one build, right? So that's something that we can work with you on, whether it be through Re3D Tech or through HP. We can do that analysis or help you with that analysis to figure out, what makes the most sense there. So I'm sorry, it's not the straightforward answer you were looking for, but it really, really does depend on a lot of different factors.
then
Just to
something
follow up
that-
on that, is he was referring to the manifold one in the previous slide.
Yeah.
Right. So I'm trying to remember. So we had some of those costs in some previous slides, and we were able to fit a decent amount of those in a build, on that order of magnitude of probably around 50 or so. And I want to say that the overall cost of that part ended up being, somewhere between $8 to $12. And this was in-house manufacturing costs. There's a lot of different factors. Again, I keep emphasizing that, but it already was at a break-even point beyond the injection molded component because of the assembly time for a pretty high volume. So that break-even point was pushed out pretty far just because of all the different components and the assembly time involved.
All right. So we got to get through these real quickly to try to get through all of them. Material limitations, I think we've spoken about that a little bit. But if you want to touch on that in terms of what ways to overcome that as an obstacle.
Right. So these materials, I would say, compared to additive materials, are very durable, very strong. They're some of the best in class materials out there in the market for 3D printing. You compare them to injection molding, they might be slightly lower properties than injection molded parts, and that mostly actually has to do with the cooling and kind of the crystallinity because of the cooling process. But without getting too much into the technical details, design can be a huge factor that overcomes these challenges. So because we have that design freedom, we can optimize parts for structural applications. Just like we saw that optimized structure for fluid flow, we can apply that same logic doing finite element analysis, topology optimization, or what we call generative design, which is another really fascinating new topic, where we can optimize that geometry for that specific loading condition, and not just get something that competes with injection molding, but is stronger for that application and lighter weight. So there's a lot of cases where just with the design itself, we can beat the properties of injection molded parts.
And then too, you'd be surprised how many times we ask, why does it need to be the material that is called out, let's say on a drawing? And a lot of reaction, well, that's what it says. And it doesn't really equate directly to the application. We can look at the material properties of what we have available additively, and a lot of times, in a lot of cases, we can move into that material set that we can offer through the HP process, just because it fits the application's need. It's not just because what it says on the drawing.
Right. Absolutely. The best mindset to approach this all with is taking a step back, not just thinking about how we've been doing things in the past, taking a step back, looking at the application itself, looking at the requirements, and kind of coming with a fresh mindset. There's a lot of even aluminum replacement that we've done in a lot of applications that I've seen, where it was aluminum just because they used aluminum in the past, but we looked at the actual loading conditions and they made a much cheaper, stronger, lightweight design with plastic 3D printing. So definitely, I would encourage people to consider it as an option.
So I think we've got a question here that covers a lot of these topics, from cost to production speed. Can you provide an example of a product that has been taken from ideation to production, the costs involved as compared to traditional manufacturing, and the speed of production compared to traditional manufacturing?
Well, we had this one part for one of our customers that we've taken, we helped them redesign it. They were milling it out of aluminum, and it was a very expensive part to mill. The reason they had it out of aluminum was because they needed robust mechanical connections. So what we did is we helped redesign that part. We took a lot of mass out of the part. We kept its strength profile with generative design. And then we also put 11 heat set inserts to those areas that we needed to have that strong, robust mechanical connection. We've made about 8,000 of these parts over the last 2 years, and we've saved, I think it was about $30 per unit on that single application. So do the math. That was a significant savings, And what we also were able to offer them was, staggered releases of those parts. Cash flow management. For a lot of businesses, when they have to do an injection molded route, they have to put all that money into the tooling and all that money into that first run of parts, where we can feather that need, that inventory need. Say they need 1,200 parts a year, we're doing 100 parts a month, and they can pay as they go. So we offer that kind of cash flow management to a lot of companies. That's very effective.
Okay, great. So we have just only a couple minutes left, and so I just want to touch on a couple things. As I mentioned, this will be available on Read 3D Tech's YouTube channel. I've just put the link for that in the chat. I notice there's still a lot of questions left on materials, and some other questions as well in a little bit more general terms. There's 2 webinars that we've done very recently. One, we did an entire webinar just on materials, so I recommend checking that one out. And then we also did a webinar back in October on 3D printing versus injection molding. I think those 2 webinars will answer a lot of the questions that we have left here, but these will also be shared with these guys here, and someone will follow up with you afterward to make sure that all of your questions are answered. You can also check out these guys here, connect with them on LinkedIn using the QR codes, and follow up with them directly with any questions you might have. So I think that's it. Thank you, everybody, for joining us, and hopefully you'll join us next time.